This next section is 15.1. We're in the general chapter or subject area of linear superpositions of waves, interference of these waves, and how we get music. What is music in terms of the sense of sound, stimulates our ears and our emotions. And our first topic here is the concept of linear superposition. Linear superposition is a very important principle in all of physics, and it basically says that the total is the linear sum of the separate components. This does not hold in the social sciences, but it does hold in the physical sciences. In particular, with waves, we simply add up these waves and we get what are called constructive and destructive interference. And let me show you how that arises. Linear superposition for waves is the total amplitude at a point is going to be the sum of the separate waves. And if these waves come along and are in phase with one another when they arrive somewhere, then the total wave will be twice as great. If, however, one of these waves is out of phase with the other wave, then we get what is called destructive interference. So if we have this wave and this wave, then in fact, they'll cancel each other out and you get no signal at all. Most normally, we get one wave, which might be like this. Another wave might start out being in phase and then get out of phase because it has a different frequency or it went through a different path. And if we do that, you can see if we added these two, they'd add up to be very large at first. Then, of course, by this time, they're getting smaller. Then, in fact, they cancel out to nothing right here. And then they begin to increase again. And so you get things that look like this, where the waves are in constructive interference, then destructive, then constructive. Right there in the middle for a while, they may totally cancel with each other. And if the wave proceeds by two paths, the phase difference can give us this constructive or destructive interference. And for example, if sound goes through two doors, sound that comes through this way, that's a wave, and the sound that comes through here from a single source, as these reach different points, then of course the oscillation went different direction, went through different lengths, and therefore they'll be out of phase or in phase. The same can come when you have two speakers. So if you have two speakers, depending upon where you sit, you can get interference between these waves that don't give you a good quality of sound. It turns out that this principle of linear superposition is extremely important in physics and sound. It applies not just to waves, but it also applies to electric and magnetic fields, gravity, and all of the forces. And these are the sums of these separate fields of forces, and they're added together and computed from the separate components. So for example, if I know what the electric field is from one source, there's a positive charge over here, and then if I knew that a separate source over here was a negative charge, and the electric field due to it would be this, then if I put both of these charges here at the same time, the total field is exactly the vector sum of these two separate vectors. And if I put more, then I simply add the vector sum of all of these different components to get the total of the magnitude and the direction. Also, I would like to talk about two other effects that we have. And these are the concepts of transverse waves and longitudinal waves. It has to do with the direction of the wave vibration relative to the motion that distinguishes these two types of waves. Let me first of all do transverse waves. What is a transverse wave? An example of a transverse wave would be like an electromagnetic wave, where the wave is traveling this way, but the electric field would go up and then go down, then go up and then go down. The motion of the wave is perpendicular to the velocity. The same is true if we have a water wave. If this is the surface of water and have a water wave that comes by, It's traveling this way, but the water moves up and down. You can tell that that's true because if you put your float out on the water, the float will go up and down. So surface waves, electromagnetic waves, and surface waves are both transverse. Now there's another type of wave, longitudinal. A longitudinal wave, as I discuss here, is where the media vibrates parallel to the velocity, and sound is an example of that. So if I speak, then the sound goes out in waves, and actually what this is it's a compression and a rarefaction. So if I look at the air molecules, they're highly compressed, then they're spread out, then they're highly compressed again. So the wave may look like this in one representation, but actually it's a compression. In other words, the sound is going back and forth, compress, expand, in the direction of the motion. And that's why it's called longitudinal. Sound is generally longitudinal as a wave. Then there's another type of wave, and it's a torsion wave. It's very, very rare, and you're very unlikely to see it. It's not that important, but it's a twisting wave about an axis. So, for example, if I have something that hangs down, like a weight, and I take this, and it's attached to the ceiling on a wire or something, if I take this and turn it, then it'll turn back and oscillate back and forth, giving a tension on this wire that will travel back and forth. And we could say that that's a torsion wave. This is the least important. These are critical to know how they're defined and examples of each. Transverse wave, the components of the wave move perpendicular to the velocity, and longitudinal, they move parallel to the velocity. Example of transverse is electromagnetic or water surface waves. Longitudinal, an example is sound. Sound compression waves.